Okay, good morning. So today we are going to look into unsymmetrical bending. Okay, but before I do unsymmetrical bending, does anyone know the difference between symmetrical and unsymmetrical bending? Anyone, please? You can type your answers or you can speak to me. Anyone? Can you remember? When do we classify symmetrical and unsymmetrical and how to differentiate them? Anyone, please? It's too early. Okay, so let's look at symmetrical. Okay, let's look at central and neutral axis not in the same spot. That is eccentric and centric loading. Tyler. Okay, so let me. You are also partly right. Okay, central and neutral axis not in the same spot. You're also partly right, Tyler, regarding that matter. Okay, so let's look at uh pure bending or bending again. Okay, so now if we have a structure, I'm going to show you two structures. Okay, two structures. Okay. So one of the structure is going to be, hold on, I'm going to copy, I'm going to paste. Okay, so this is our usual point A, point B, point A, point B. Okay, and then one of the structure on the left hand side, you have evenly distributed load. Okay, you have evenly distributed load, where you have omega Newton per meter. And the other one, you don't have evenly distributed, you got a gradient distributed load up to a certain point. It stops. Okay, and I'm going to call this, it will stop at point C. Okay, and then after that, you have a point load coming down here. And this point load is coming down at point D. Okay, now question for you all. Which structure is under symmetrical bending and which structure is not under symmetrical bending? And before I ask that question, I draw the transformation. So this is X, Y, this is rotation about Z. Okay. So Trevor say left is symmetry, R is not. Okay. So those of you that agree to Trevor, put a thumbs up. Okay. I agree with Trevor. I agree with Trevor. Okay. Right. So on it's okay. Wow. Right. So on the left is symmetrical. So for now, okay, for now, we think that the left is symmetrical bending, the right is symmetrical bending. The right is not symmetrical bending. Okay. Right. So we know, okay, we know to find the I'm not saying which one is or not yet. Okay. So we know that the formula to find whether is it symmetrical bending is stress X is equal to mz over izz multiplied by y. Okay. Then I'm going to I'm going to draw again 3 different cross-sectional area. Okay. Let's say these 2 loading condition. I'm going to draw another view regarding the cross-sectional area. Okay. So now I'm following this transformation. So this is Y, this is Z, okay, and then this is my rotation about X. Okay. So you have cross-sectional area 1, Okay. So cross-sectional one, you have a T. Come on, Eugene. Good morning. You have a T section. Okay. And then I'm going to draw the geometric axis of symmetry. Then I'm going to have a cross section number 2. Okay, so cross section number 2 looks like this. So it's a N or a C. And I'm going to again draw the axis of symmetry. And then cross section number 3. Okay, I'm going to draw a cross section that is I. Okay, then I'm going to draw the axis of symmetry. Yeah, I'm partial colorblind. I can't see my colors at all. That's why my chemistry, I can't make it, okay? They mix the solution and ask me what color, I can't tell. Sometimes I try to taste, it won't work. Right. So now, by looking at the loading condition, okay, the one on the left, on the right, okay. So from here, I will say both of them, okay. So I can say both of them are under symmetrical. Okay, so sorry, I won't say both of them are under. Yeah, I will make this statement. So both of them are under symmetrical bending. Okay, so the left and the right, both of them are under symmetrical bending. So i.e., now some of you are just say, hey, this is confusing. Okay, so whether symmetrical or not, okay, whether symmetrical or unsymmetry is not dependent on the load or loading conditions. So does not matter whether it is does not matter if it is evenly distributed, gradient with point out, does not matter. Okay, but it is dependent on the applied moment. What do I mean? Okay, for symmetrical bending, okay, the applied moment must be acting in one direction only. Okay, one direction. So i.e. is either my, okay, it's either my or mz. Okay, it's either my or mz. You cannot have both my and mz. If you have both my and mz, it's unsymmetrical already. Okay, now next question is this. Okay, next question. So now I give you. So let's call this. Let's imagine. Okay, let's imagine. Okay, the both above loading condition, right, have three cross-sectional area. Okay, cross-sectional area 1, okay, cross-section 1 that looks like a T, and we have an axis axis of geometric axis of symmetry about the YY axis. Cross-section number 2, also YY axis. Cross-section number 3, axis of symmetry is on the YY and on the ZZ axis. Okay, now I will again ask you the question. Based on the cross-section area, okay, based on the cross-section, so my question is this, okay, read my question properly. So based on the cross-sectional area, okay, cross-sectional area, okay, which one is under symmetry bending condition. Okay, so I want you to look at these three cross-section. Okay, oh, I do apologize, too excited again. I want you to look at the three cross-sectional area. Okay, now from the cross-sectional area, right, can you tell me which one is under symmetrical bending? Number 1, 2, or number 3? Now, watch it, okay? It is all dependent on this formula over here. Okay, it's all dependent on this formula because we only have moment about the z-axis. So we already clarify by looking at the load distribution, right? Whether is it evenly distributed load or gradient distributed load, we cannot tell, or it's not dependent on how the load is distributed, but it depends on the applied moment. So the applied moment must be either along my or mz. Now let's look at the cross-sectional area. Okay, cross-sectional area 1, cross-sectional area 2, cross-sectional area 3. Okay, can anyone tell me, or can anyone, or just put down there, who says cross-sectional area 1 is symmetrical bending? Anyone? I don't see any thumbs up at all. Okay, if you agree, one person say thumbs up. Okay, and a few of you. How about cross-sectional area 2? Is it under symmetrical bending? Some of you put yes, some yes. Okay. How about cross-sectional area 3? Okay, a lot of people seems to be reacting a lot to cross-sectional area 3. Will it depend on the direction of the moment? Jihan, that is the question. Jihan, as long as, okay, as long as the moment is applied in my or mz, it cannot be. So if it's just my, it's symmetrical bending. If it's mz, it's symmetrical bending. Okay, it cannot be both. Okay, Jihan, you understand? If you understand, just put a smile on your comment, please, or give me a thumbs up because I'm waiting for your response. Is that okay, Jihan? So if it's both, Jihan, also if it's both unsymmetric, yeah. If you have my and mz together, it's unsymmetrical bending, and I'll tell you why later on. Okay. Now, let's look at this cross-sectional area, cross-section. So by looking at all of them, okay, all of them are symmetrical, under symmetrical bending. All of them. So some of you say, oh shit, why is this, right? The thing is why is this, okay? Now I'm going to call all this point, okay? So I'm going to call this point. I'm going to show you why, okay? I'm not going to tell you this is so and just leave you out to dry. Alpha, beta, alpha, beta, alpha, beta. Okay, and I'm going to call this I,